Hey friends, here at Handsome Minutes, we really appreciate our sponsors. And I'm talking to JD from Raygun. JD, why monitoring? Why do I need to monitor my production applications?
Well, first and foremost, we obviously want to deliver a great experience to our users. And as a developer, when I'm working on my machine and something breaks, the debugger hits, I can fix it really quickly with all the context there. So we wanted to answer the question, how do we deliver that same experience, but in production, where everything that goes wrong gives me all the context to go and fix those issues really quickly for people?
Absolutely fantastic. You can go to raygun.com for a 14-day free trial and use the code Hanselman for half-price monitoring for your first month. Hi, I'm Scott Hanselman. This is another episode of Hansel Minutes in association with the ACM Bytecast. Today, I have the distinct pleasure to speak with Dr. Wen-Mei, who from NVIDIA, from the University of California, Berkeley. You got your PhD in the 80s. And then do you also teach at the University of Illinois at Urbana-Champaign, sir?
Yes, I taught there for 34 years before
my goodness.
I graduated and went to NVIDIA.
That's wonderful. So you have a wonderful paper that we'll put a link to in the show notes called Running on Parallelism and a few lessons learned along the way. And I love that it starts on the first slide with a list of years and people. It's so refreshing and wonderful to see an acknowledgement of the history of the space as the first slide. Was that a conscious decision to lead with that?
Yes, this actually was the set of slides that I used after I received the ACM IEEE Ecker-Markley Award. And basically, when the committee chair called me, told me that I would be the recipient. It took me a little bit of time to accept it. If you look at the list of people that I had, these are the people who literally were building the historic machines and the publishing extremely influential work along in the history. Many of them are the authors of the textbook that I read when I was grad student. So I wanted to put that slide up in the context before I talk about any thoughts after receiving that award, that these are the people that I was standing on their shoulder while I do my work.
That's so wonderful because it's such an amazing group, and to be acknowledged in the same list, in the same breath, going back so many years must feel really amazing. The discussion is about parallelism and where it fits into like the historical context of things. And if we think about Moore's law, throwing transistors at the problem, and maybe starting to flatten out, we're seeing computing in general start to move towards not just parallelism, but massive, massive parallelism. Is that because we're starting to hit some physical limitation, there's some quantum limitations? We can only throw so much power at these things. We have to start to go wide.
Yeah, I actually kind of lived through the whole cycle in my professional career. When I started as a grad student in 1983, it was really I would call the real beginning of the Moore's law. And later on, we also understood Dennard scaling. And these two things, are kind of incredibly important for the next, I would say, 20 years. So the Moore's law basically drives the industry to reduce the transistor size every, you can argue 18 months or 2 years. And so basically, that allows people to pack in, twice the amount of transistors per chip without increasing the size of the chip, right? That's economically very, very good. But from my career, Dennard scaling was even more important. Dennard scaling, as you reduce the transistor size, you will reduce the voltage by the 1 over square root, and you reduce basically as a result, you can reduce the power consumption per chip area by 1 over square root, and you can improve the speed of the transistor or reduce the switching time and time by 1 over square root of 2. And you can still have more transistors, right? So that is incredibly important, because for the next 15 years, people literally say that they can write a piece of code, go to sleep for 5 years, and wake up. That piece of code will run much faster without doing anything to it. And this is great because during my grad school days, we actually, I went to University of California, Berkeley, and that was a time when we really debated what the future course of microprocessors will be. That's when Hennessy and Patterson were advocating RISC, and that was there were a huge number of discussions. But the research group that my advisor, Yale Pat, and some of my fellow grad students look sort of beyond the immediate next 5 years and look to the 10, 15 years and say, well, if we have so many transistors and these transistors are going to be running so fast, how about if we use these transistors to detect the parallelism that nobody can currently detect in their processors, and use the parallelism to run things much faster? So, and we got lucky. We got lucky that by 1993, when Intel designed the first P6, the Moore's law and Dennard scaling got to the point where they can design such a processor based on some of the intellectual research we did in the 1980s, and many, many other people did after us, so that they can build the P6, which is the Pentium the Pro processor. And that processor embodied all the parallelism mechanisms that we envisioned. And that was history. And one of the interesting lessons we learned is that when we do research, we really need to understand where the technology is going to be 10 years from now, because by the time people put any of your research ideas into this hardware, it will be at least 5 years, if not 10 years.
Yeah. So for folks that are listening who may not be familiar with some of these terms, I want to call out some things that you said that folks can go and read more about. So Dennard scaling, also known as MOSFET scaling, that was 1974 when that was being thought about. And that held, as you pointed out, for 25 plus years until it started to kind of falter in the early 2000s there. And then with modern GPUs, you're looking for ways to get around it, stacking chips, coming up with new ways to cool, because you may be getting higher performance without power consumption, but you're still getting power leakage, you're getting heat dissipation, you're pushing up against the laws of physics itself. You say, though, you're thinking 10 years out. Is there a limit? Is there a possible theoretical limit where you will actually say, nope, that is as far as this is going to go?
I think there is, but we don't know exactly when it's going to hit. This is like a stock that keeps going up. Everyone says it's going to go down at some point, but nobody knows when, right? So we have been saying that the Dennard scaling will be ending, which ended. So the whole Dennard scaling ended in early 2000, as you mentioned. But for Moore's law, we can probably see at least another 2 generations, and but we are already at the point where we're building computers very differently than scaling on the chip. And Scott, you already mentioned that we try to get a stack memory. We try to do the chip packaging, but I think most of the innovations today, if you look at what the big innovations are for today's research, we are already into building very, very big systems with reasonable latency. So we're going to see big changes in networking, and especially going from electrical to optical, and we're going to see the very different system communication primitives that allow us to synchronize a huge number of machines fast. And these are all because we already have, we are already seeing that coming, right? We don't know exactly when it's to come, but we need to run as fast as we can so that we're ready when they come. And chances are we may not even be totally ready when it comes.
Yeah. This might be an interesting question or a dumb question, but we hear about people being full stack engineers, and you're probably not thinking about Node or Erlang or JavaScript at the highest level. When someone is a software engineer, for them, low level might be going into Google Chrome and hitting F12. But for you, you're starting to bump up against like protons and electrons moving around in space. But the software stack overhead has us wondering, even if as I sit here on a highly parallel machine, why does my machine feel slow?
Yes.
Are you thinking about software paradigms and how people are going to program in 5 or 10 years and applying that to how you're going to create these pieces, these chips in 10 years?
Absolutely. There are two important forces in these kind of things, right? One is reality. People, there are a huge number of people programming with Python, right? And so when we deal with frameworks based on Python, such as PyTorch, we see all kinds of interesting, not just overhead, but the bottlenecks. For example, the Python interpreter lock, right? That fundamentally restricts the kind of parallelism we can expect at the source language level. And more subtly, all the GPU activities that are launched through the Python based frameworks are based on APIs. And what that means is that these API calls are separated from each other. Okay, they're not adjacent to each other in terms of the compilation process or the interpretation process. We're seeing these individual activities. So one of the important things that we will begin to see is how the lower level software and hardware combination will be able to take these API calls and maybe doing things like fusing these activities on the fly, and optimizing away some of the inefficiencies because these are isolated events. But these are the kind of things that people have been working on for decades, and starting from the Java days, and Microsoft has the runtime compilation activities for a long time. The RT, all the runtime linker optimizers. But I think we will getting to the point where some of these technologies will begin to really be deployed in the next decade or so because we are running out of room for further optimizations without deploying these kind of techniques.
Hey friends, in the interest of me learning more about AI, for the next couple of episodes, I'm going to have a little thing in the middle where I'm going to bring Leynvert Van Doorn from Qualcomm in to help me understand more about AI. Now, at Qualcomm, you've really taken a developer-first approach at getting folks excited about the silicon that you're creating. Why do you do that?
Oh, well, developers basically add value to your platform, right? It's allowing them to enable or to use your hardware. They're going to come up with new applications. They're going to come up with new use cases that you've never thought of, and they add value to that. And the key component of allowing developers to do this is to make sure that they've got the information available that they need. And that's a big thing what we refer to as developer first at Qualcomm, but it's basically making things available so you can just download it. You don't have to sign licenses. The tools are there. The open source tools are there. That is, in short, what's developer first and why it's necessary.
Yeah, and engaging more deeply with the community. I love that you are showing up in all of those spaces. And folks can check out more at qualcomm.com/developer to download those things and learn more today. It seems like if I recall, when I was getting my first 386, there was the SX and the DX, and then we had ones with a coprocessor. And companies would say, we need to figure out something for that coprocessor to do. Maybe people will buy it if they use Excel. So then we would buy this computer because I want to use Excel. When I wanted to play Quake or Doom, I would buy a 3DFX card because I wanted that.
Yes.
When I want to play a great game now, I'll buy an NVIDIA processor. I'm on a machine right now with a 4080 Super. And I'm thinking to myself, what is that really good at that my Intel chip is not very good at? And if I look to my right here, I have a Copilot PC with an NPU from a competitor from Qualcomm. So now suddenly it's not about a CPU and a coprocessor. I've got 3 very competent, different kinds of processing units here. Do you think there'll only be 3? Will I come into a world where there's 5 or 6 or 10 different fundamentally interesting processor units that do different tasks?
Oh, I think that's $1 billion question. So I can tell you what I think personally, right? I think there will be at least one more, but this has to do with what you want to do. Scott, you hit the nail on the head. People don't want processors. People want applications, right? People buy processors reluctantly because they want to run their applications well, right? So today, I would say that people buy GPUs because they want to train models, and these models, have all these, all the training needs that people buy these GPUs reluctantly. So I think I'll turn your question just a little bit and maybe say that the reason I think there will be another kind of processing unit is because at some point people will want to be able to deal with massive amount of data on the first-hand basis. What I mean is that we are going through the machine learning era where we reduce all that data, the training data, into these models, right? And then we converted the query process into a computation inference through this model, and we get the information. But we kind of bypass the need of finding data in real time. Google has been doing search, and Microsoft has been doing search, and these search are real-time searches, right? These, if you use Bing, if you use Google, all these things are pre-indexed data that we hope to serve the user real time. And so one thing that is very, very interesting is that we kind of swing the pendulum so much in the deep learning models and the large language models that we should begin to think about what happens if people don't need to. These models have their limitations. And what if people want to be able to go straight to the data, and but use some of the model capabilities to be able to find the data much better than the first previous generation search. So I can imagine that in order to do this, we will need to have a unit that is going to be able to tolerate latency and introduce very, very efficient the ways to grab, let's say, 1 kilobyte of data out of 4 petabytes of data, right? And serve it to the user in real time, and go through some of the models to give user very digestible outcome.
Yeah, solving the needle in a haystack problem.
Yes.
At scale, because that traditionally, you mentioned this in the paper and in the presentation, this memory storage divide, it feels like the majority of the work that my computer is doing as a user is simply moving data from one format to another. It's just transformation. And that's becoming quite tedious as I simply want to work or I want to enjoy my computer.
Absolutely. So right now we have all these file system, software stacks, and so on that we built over the years that are standing in the way. And the format that you're talking about are imposed partly by these kind of software stack. But what people really want is their data. People don't want the file system. People don't want the formats, right? And how do we get people what they want? And I think that's going to be the next unit.
Yeah, and it seems like we're narrowing the space between the work and the data. We have that storage throughput, we have that latency that is being applied. We're setting up little islands where your parallelism and your data that it's running on are near each other, so as to avoid that latency, which is now down to picoseconds. It's down to nothing. It's down as little latency as possible.
Absolutely.
Yeah, I've seen you mentioned millisecond level latency and terabytes a second throughput. It seems like a dream, but it's going to happen at some point.
I really believe that if we do the work right, when someone does this interview 10 years from now, the person may have a machine on the desktop even. Right? I can see how we can build these kind of things in the data center at a very high cost. But the real test is that can we put this kind of capability into every person's desktop, or even I would say even a small device that the person carries that has the entire lifetime's memory and information that you can retrieve real time when you talk to someone.
It's interesting that you mentioned that, because just literally yesterday, and I'm going to take my headphones off and grab something off of my floor here. Just yesterday, a friend of mine sent me a package. And for those of you who are listening to this podcast, you won't see this, but I'm holding up a compact PC companion. And some of these early devices, the Palm Pilot, we've always wanted our life, our family, our friends, our photos in a tiny device like this.
Yes.
And I was there. My first applications were on the Palm Pilot. This is a pocket supercomputer with its own GPU. And now we're going to see AI start to move its way into our pockets. The idea that what once filled a room is carried around with me with all day battery life. And to your point, the data won't be in the cloud. It could just be in my pocket.
Exactly. And I can see how that can happen. I work with a lot of the SSD storage vendors, on a regular basis. I work with, some of these, the PCB builders, and then, some of these, the mobile chip builders. I can see that if we do the right things, within a decade, we can begin to have these devices that truly extend us, right? I really feel that the real benefit for these devices is to make each of us a infinite memory capable person, and it can complement some of the let's say, just like calculators complemented our way to do arithmetic. We should be able to remember the names of all our the associates and colleagues and so on in real time, no problem, right? Now I can't.
So. I was looking at some pictures of a former U.S. president who was being introduced to some dignitaries, and you could tell that someone was whispering, "That's the president of France, and this is his wife, and their children's names are." That's what I would like for my coworkers, for my colleagues, for people I haven't seen in 10 years, is someone to whisper in my ear. But right now, to do that, I have to go to the cloud, interact with a vendor. That's fast, sparse access to massive data.
Yes.
And who knows what that costs in power consumption. As I go to Google Photos today and I say, show me pictures of my child in the snow when they were 2.
Yes.
You're saying that algorithms, memory capacity, the theoretical limits will happen such that we could have that in our pocket.
Not only that, you don't need to scroll through 100 results and pick the best one.
That's amazing. That's what I want. But that's going to require silicon changes. It's going to require algorithmic changes. That's beyond a generational shift. That's going to get the entire industry to head in a different direction.
Yes or no? we have been witnessing these kind of things. If there's enough value, these things move fast. For example, I have seen the whole GPU the movement. Where I still remember in 2011 when we proposed to build a supercomputer called Blue Waters based on GPUs to NSF, and there was a review panel, and people, these review panelists were all supercomputing center directors who had decades of experience building supercomputers and serving communities with supercomputers, right? And after my presentation, the person, one of the panelists said, this proposal is risky to say the least, and probably irresponsible, if you really look at it. And so I said, why do you say this? He said, compare the number of math library functions that GPUs have versus the Intel math kernel library, right? And you're ways away from that. And I said, yes, but we know that there are only a limited number of science applications that people truly care about using supercomputers. We know that this is going to start with more special purpose. But if you look at the computational speed over wattage, this thing is a small puppy with big paws. Okay, and let's take that step. And somehow, by miracle, that panel agreed, allowed us to do it, right? And 13 years later, we're sitting here looking at all the math libraries that people already built. And if you look at the model training process, people put together multiple generations of these kind of frameworks over the past 5 years, right? If it provides enough value, if there's enough incentive, it will happen.
That's amazing. Like there's the people who have the audacity to do it once, to propose a petascale supercomputer, to get the National Science Foundation to think it's a good idea, to give you $200 million to do it, and now it's being done by others, and that's unbelievable.
Thank you.
Yeah, thank you. And then now, is it the Delta project that is the next step of Blue Waters?
The Delta project is not meant to be it is the next step of Blue Waters in the sense that there's a real academic need for more of these GPUs, and there's a serious shortage of GPUs available to academic researchers today. And so Delta is meant to fill that gap. But Delta is not like Blue Waters, where we know there's so many known risks. We know there's so many potential failures that can become scandals for the public. And we had to to work with all the science teams and all there are 4 science teams that I'm eternally grateful how much work they put into their applications to move them into GPUs and prove the benefits. And Cray and NVIDIA dedicated hundreds of people working on this project to make sure that it does not fail, right? So Delta is not at that kind of level. Delta is really about how we can enable the poor academic researchers who really need the GPU time to be able to make some real progress in their.
I see. So it's about access to those resources more than it is about pushing the boundaries of computational power.
Exactly.
Okay. What projects are you excited about where folks can go and learn about supercomputing projects and, audacious moonshot type things like that are going to take us into the exaflops?
Yeah. So there are several exascale projects, that is coming together, and I would say most of them have very interesting ideas. But I think one of the biggest challenges that all these supercomputers are trying to figure out is this whole networking, because we do have the option to build optical networks. But these optical networks are so expensive; they are more than 10 times more expensive than their copper equivalents. That's why whenever the distances are short, these optical connections are not used. And so I think if we look at the next generation, we're going to see I would say big movements in terms of the network connection and in terms of the cooling. We're definitely at the cooling limit for all the machines. I still remember that when we're calculating the amount of water that we need to pump through one of these data centers, and I said, can we really have that much water? I think some of the exascale machines would have very interesting the cooling mechanisms, and these things will be published soon as soon as these machines are operational.
I'm trying to think about what I'm going to do as I retire, as I think about retirement, as I think about what are the next 50 years going to be. Are you going to be doing this until you can't walk anymore? Are you going to do this are you going to be a parallelism person and a computing pioneer until the end?
I might.
Because you seem like you're having a lot of fun.
Exactly. And Scott, let me tell you when I think I'm going to retire. I will retire when I have that device in my hand. And, and I can go around and show people, pretend to be the most intelligent person on earth, and spend my time explaining to people how they can use this device.
That's wonderful. I hope we both get to see that happen, because that is the promise of a pocket supercomputer that really makes your life better, makes your relationships better. It is about the things you can do with it. It's about the people and the connections. Absolutely.
And I really hope to live to see that day.
Fantastic. Thank you so much, sir, for chatting with me today.
Thank you, Scott, for this opportunity.
I have been chatting with Dr. Wen-Mei. He is the Senior Director of Research and Distinguished Research Scientist at NVIDIA Corporation. And many congratulations as well, sir, on your award, your ACM IEEE award, for your pioneering contributions in the design of these processor architectures. We do appreciate you and all of the work that you and your colleagues have done to move us forward in computing.
Thank you. Thank you so much, Scott.
This has been another episode of Hansel Minutes in association with the ACM Bytecast, and we'll see you again next week.